Here's a lab I really enjoy doing with my students. It's a target lab, a lab in which they are putting a mark on a graduated cylinder and hopefully generating just enough gas to land on that mark and get graded accordingly. It's one that involves stoichiometry, gas laws, and nice prediction and observation making. So I'm going to start by showing you the setup here. This is a gas collecting trough. It's filled with water, and I've got a tube going into the sink that's for the overflow, but it's filled right to here with water. Have a graduated cylinder that I'm going to fill with water and invert. That's a little tricky. I'll show you that in a second. And here is a Erlenmeyer flask, 1-hole stopper, and some tubing that's going to go into here to generate the gas, going to collect it in this graduated cylinder. So here's the trick here. We're going to start with placing about, and that's why I have these gloves on, about 100 milliliters of, now the concentration of this, anywhere from 6, 7, 8, 9 molar. You can't use it too weak because it'll go too slowly, and one of the benefits of this is you can do it pretty quickly. So I've got this as 9 molar HCl, and I'm just going to put approximately 100 milliliters in there. Okay, stopper that up, put that off to the side. That's the reason I was wearing these gloves here. And now I want to be able to get this all set up and ready to go, but not have the reaction start yet. So here's what I'm going to do. I've got a piece of zinc metal, okay, and placed on the scale here, and it weighs 2.35 grams. Okay, we'll remember that, 2.35. That'll come up in a bit. And I want to put it in that flask in a way where it isn't yet reacting. Well, here's an idea. I can take this magnet and have the zinc held in place right there inside the flask without it touching the HCl. Well, unfortunately, zinc is not very ferromagnetic. It's not strongly attracted, but I've got a paper clip made of iron and coated with plastic that is going to help me do that. So I'm just going to kind of ball this up a little bit and put the paper clip on it. Okay? And so I'm lowering this in there, but using the magnet to hold it in place, suspended above the HCl. That's a nice little design. The students appreciate that. It gets all exciting. Ooh. Okay. Now, let's fill this graduated cylinder up with some water and invert it into there. That's a little tricky. So here it is. If you don't have a sink deep enough, because my sinks aren't this deep in my chem lab, you simply take a cup and fill it up several times to get this filled up. But I'll take advantage of this nice deep sink, fill my graduated cylinder up, and I mean all the way. Okay? And now we want to take a piece of plastic wrap and just cover the top of it, trying to get no bubbles at all in there. Okay? Now, as I turn this upside down, the plastic wrap stays in place. Once it's in the water, I can take the plastic wrap off, and I've got my graduated cylinder inverted. Now, there's a little bench for this to sit on here, so I'm going to lift it up and rest it on there. And because I think you know why I'm going to use this ring stand to hold this in place, I wouldn't want this tipping over in the middle of the experiment. Okay? So, there's my setup. And I've got it so that the increments are facing you guys. Okay, we're good to go. This is the delivery tube, okay? And I'm just going to slide that up underneath the graduated cylinder and kind of pinch it in place there. I don't want that to come loose. So the question is, if that much zinc reacts with excess HCl, and that's like 10 times more HCl than it needs, what volume of hydrogen gas will be produced? I'll do the calculations for that on the board. But rather than just have that be the prediction and they do, oh, here's what we're going to do. I know it's going to be in the 800, 900 range. Oh, let me turn this. This has the wrong increments facing you. They're the ones you want. Okay? I'm going to dry off a little patch right here. And I made a bunch of these on a piece of acetate, like for the overhead projector. I'll hold that up there so you can see what I'm talking about. Okay? Those are I printed off one of them. That's enough for like 10 years of doing this lab because all I need is little tiny strips like that. So I'm going to cut off one of those. Okay. And once I've predicted from the math how much gas this is going to produce, I being the student now, I'm going to tape that right to the graduated cylinder. And once that's done, it's taped there, now you've locked in your prediction, right? Then we pull the magnet away, and the zinc, well, you'll see the zinc falls in, we bubble the hydrogen up, and the water level, or the gas level, is going to tell them their grade, okay? This is out of 10, okay? So we'll come back to that after we do the calculations here. 2.35 was the mass of the zinc. We have to be able to convert that into moles, so we're going to divide that by 65 point, let's see, we had 65.409 grams, looking at the periodic table there. But we don't want to stop there. We're not talking about how many moles of zinc. We don't want to know how many moles of hydrogen. So a little sidebar here. What is the reaction taking place that's going to be taking place? They've already studied predicting products. So zinc plus the HCl that's in solution in the flask is going to produce zinc chloride plus hydrogen gas. It needs to be balanced. If it's not balanced, it's not a correct recipe, but it's actually a pretty easy one to balance. And this is nice. They've actually already seen this exact reaction in another target lab earlier in the year, in which they were just trying to figure out how much zinc chloride would be produced after the water was evaporated off. And now we come back to the gas laws chapter, and we're looking at how much hydrogen's produced. So here's our, what I call the stoichiometry step. Moles of zinc on bottom, moles of hydrogen on top. And okay, it is just a 1-to-1 ratio, but that's still important that they do that. If it had been some other ratio, that's where that would go. And we stop there and figure out how many moles that is. 2.35, essentially just divided by 65.409. 0.0359 moles of hydrogen. Now, how do I figure out the volume? What relationship is there between volume and moles? Well, a mole is 22.4 liters, but that only works at STP. And we're not at 0 degrees Celsius here, and I'll assume we're at about 1 atmosphere. Okay, if you had a barometer in the room, that would be a good place for it. A little side note, you might think you can just call up a local weather station or go online and find out the barometric pressure. It turns out that that barometric pressure they report is not the actual pressure. It would be the pressure adjusted for sea level, and you'd have to actually calculate from that how far above sea level you are. Most people don't realize that. Barometric pressure that's reported in news and weather forecasts is not the actual pressure. It's been adjusted for that location being at sea level. Otherwise, like Denver, Colorado would always have really, really, really low pressures, but they don't. Go online and check out what the barometric pressure reading is in Denver right now. It's pretty much the same as it is here because it's been adjusted for sea level. So, but we're just going to assume 1 atmosphere, 760 torr a day. The equation, of course, that relates these is the infamous Pervnerd equation. PV equals nRT. So we have a pressure, I'm going to assume 760. Volume, that's what we want to find out. Number of moles, we just figured that out. 0.0359 moles are 62.4 liter torr per mole Kelvin. And the temperature. I had a temperature probe over here. When I turn it on. How easy is this? The temperature in the room right now today, 25 degrees Celsius, 25.1. So we'll call that a 298. Kelvin, of course. There we go. Now, when you figure out the volume here, I still have this number in the calculator. A lot of students want to clear something. As soon as it shows up, they want to clear it. Right? Why? It's the next thing I want to enter. So we'll keep that on there. Times 62.4 times 298 divided by, and I know this is just kind of approximated, but you know what? We don't really experience a huge range in pressures. 760 is pretty close to what we are at right now, especially if you're near sea level. I'm getting a volume of 0.879 liters. Okay? Now, two problems with that number, two correction factors. One is that as this gas is collected, it's not pure hydrogen. There's water vapor in there. Another problem is that gas won't completely fill the tube all the way down to the water level here. So maybe it'll stop in this range here. There's a column of water that is actually, you can think of it as pulling down, but it's not really. It's creating a lower pressure inside. Those two factors combined are going to make that airspace, the fact that there's water vapor in there and the fact that there's this water column pulling down, is going to make that gas pocket about 9% bigger. Now, with an advanced class, you can go ahead and do the vapor pressure calculations. With my lower level Chem 1 students, I just essentially say, take that number and add 9% to it. So we're going to multiply it by 1.09, and that's going to be true across the board for every prediction they make on this. So times 1.09, and we're getting 958 milliliters. It says, sorry, 0.958 liters is what it says, but I know that's going to be 958 milliliters. Okay? So let's see if I'm on target today. Okay? Here is my taping of my prediction. I can make sure it's right side up for the camera. Oh, some of the numbers just came off. Let me cut another one just so we don't have. Okay, so I'm going to tape it so that that 10, the perfect score is at the 958 millimeter mark. And I'm going to have to come around here to do that. So it's an upside down scale. I've got 950, there's 960. So I'm going to tape this right there. Actually, I'll do it on this side so the camera can catch it better. I'll move it over. 958. Okay, and we'll rotate this a bit for the sake of the camera. Okay, the camera picking that up? Okay, so here we go. Notice I have this set at a pretty high concentration, so we'll find our results pretty quickly. Okay, here we go. Reaction starts up. The gas is being produced here. You're saying, what about that fog? I thought hydrogen's an invisible gas. It is. I've got such a strong HCl concentration here to make the reaction go rather rapidly. And you don't have to use that high concentration if you don't want to. But it does create a little bit of HCl vapor. Tiny amount, but it does show up when it then condenses. I mean, it combines with the condensation. But here we go. This is still relatively pure hydrogen. You're seeing some of the water vapor in there. And, uh-oh, we're getting nervous now. Is it going to pass the mark? The students are all, they don't know what to think here. One last little piece there, still clinging away. Can we get a picture of close-up on that on the camera? There's still a little tiny piece bubbling away here. It got caught in the wedge of the paper clip. The paper clip, by the way, is not reacting. It's covered with plastic. And we want that to completely react. I can give this a swirl. That's not cheating. That's not. That's the gas that's supposed to be over there. How did I do, Teach? I'm in the 10 range, I think, yeah? Okay. So, it's a nice little reaction. You got this generated. That'll clear up in a few minutes, but I'm actually not going to let it. I'm going to do something else with it. If you don't want to go that fast, we do that mostly for the videotaping. You can have it go much more slowly than that. Use a lower concentration here. It'll come out nice and clear. Be more suspense. The students could actually probably, if you had a lower concentration, take this away while it's reacting, do the calculations. It's still bubbling, they put it there. But I think it's kind of better to have no idea whether it's going to be 10 milliliters or, well, it can't be past 1,000. So anyway, nice little lab, target lab, and of course, I'm a sucker for this. I can't generate a 958 milliliters of hydrogen gas and just let it go to waste. So here's how you take this down. Okay, and we're going to, ready? You might want to cover your ears. This is a little loud. It's not that loud, though. 1, 2, 3. Thank you.